Welcome back. With this segment, we're going to start a new unit, and this will take us away from elliptic problems. We're going to start looking at parabolic problems, right? And we're going to stick with linear parabolic PDEs in 3 dimensions, but for a scalar variable. The kinds of problems we're looking at, therefore, are very similar to ones we've already considered. They are the unsteady heat conduction problem in 3 dimensions, or the unsteady mass diffusion problem also in 3 dimensions. You will recall that previously we studied the steady state versions of these 2 physical problems, and because we were looking at the steady state versions, those particular PDEs are what we call elliptic PDEs. When we bring back the time dependence, when say they're unsteady problems, we have parabolic PDEs. Okay, so with that somewhat verbose introduction, let's get on with it, right? Linear parabolic PDE in a scalar variable in 3 dimensions as well. Okay, and like I said, the physical problems we are considering here are unsteady heat conduction and mass diffusion. In 3D. Okay, and just remember that unsteady here means that we're talking of time dependent. All right. So, what is the situation we have here? I don't have with me today my basis vectors, but we don't really need them. We have our body, right, and we have basis vectors here. It's 3-dimensional. Everything that we talked about, the steady state heat conduction problem holds. Okay, so we have surfaces on which we are going to specify Dirichlet and Neumann conditions for the temperature if we're doing heat conduction, or the concentration if we're doing mass diffusion. That's fixed. Okay, that remains the same. We have a source term. We have the notion of the conductivity tensor or the or the diffusivity tensor. All the same. The additional component is that we are saying now that at every point in the domain, either the temperature, if it's a heat conduction problem, or the concentration, if it's the mass diffusion problem, is changing with time because of fluxes or because of the source term. Okay, so at every point we will have in addition a time-dependent term. It's going to be a first-order time dependence because that is the nature of parabolic problems, right? And that is indeed the nature of the time-dependent or unsteady heat conduction and mass diffusion problem, right? They're first-order in time. Okay. So, with that setting, let's essentially write out the strong form. Okay, and as we've been doing, let's begin by drawing a picture, a figure. These are our basis vectors, E1, E2, E3. All right, our domain is that, right? 3-dimensional, of course. We have 3 basis vectors here. omega, right? Somewhat mercifully, perhaps, we are back to a scalar problem, right? So we don't need to worry about the three different decompositions of the boundary, right? So we have here partial of omega u, right? Because u is now a scalar once again, and here we have partial, I believe omega j is how we denoted it, right? All right. Now, a point here has position vector x, which we will use, right? And at this point, the picture here, the usual pillbox argument that's given is the following, right? We look at a little elemental volume, okay? What we see is that we have fluxes coming into it, okay? And since we've already introduced the notion of a flux before, we can use it now, okay? So we have fluxes coming into it, and for certain they could be exiting some part also, right? So, right, so on. So this is our flux vector j, okay? Now, inside that little volume element, we have some source term. And that source term, you recall, if we are dealing with a heat conduction problem, would represent local heating, right, through some external source. Or for the mass diffusion problem, it would represent a local supply of mass. Okay, so let me write an F if I can there. Okay, that's F. Now, what we're seeing in this unsteady description of the problem, the description of the unsteady problem, is that the result of the fluxes, the net flux into that volume element, and the effect of the source term, their combined effect is to change either the temperature per unit time, right? With respect to time, either the temperature changes or the concentration changes with respect to time. Okay, so let's also add in here essentially just to portray this, let me say that there is a du with respect to dt term also coming up, right? T, of course, is time. Okay, so the strong form is the following. As always, given the data, given I think we were still calling it UG back then. We had Jn, which is our influx condition. Our source F, right? And the constitutive relation that we are now very familiar with. Right, using coordinate notation, kappa ij being the conductivity tensor, right? Given all of this, now we have one extra piece of not quite data, but it really is a coefficient that's relevant to the problem. And I want to put it down here to have relevance to make connection with the physical problems that we are trying to keep at the back of our minds, right? The heat conduction and the mass diffusion problem. That quantity is going to be denoted as rho. Okay, I'll tell you once we set up the problem what rho is. Okay, so given all of these, what we're trying to do is the following: find u, okay, such that the following holds, right? Rho partial of u with respect to time equals minus j I comma I plus F in, now here's, this part is important. When we were doing the steady state problem, we specified all our previous problems were time independent, right? They were all steady state problems. We specify the PDEs, therefore, only over a spatial dimension, over a spatial domain omega, right? Subset of R3 in general in the 3D case. But now we have time dependence as well. So we say that this PDE holds in a combination of the spatial dimension, of the spatial domain and the time interval of interest. And that is indicated by a cross 0, capital T. Okay? So the closed interval 0 to capital T is our time interval of interest. Okay, and when we write omega cross that time interval, we are just saying that our PDE holds over a certain spatial domain, omega, and over a time interval 0 to T. Okay? All right. As before, we have boundary conditions. We have U equals UG on the Dirichlet boundary. We have our Neumann condition minus Ji Ni equals J sub n on partial omega J. Is our problem complete with specifying boundary conditions? No, we need initial conditions as well, right? Because it's a first order problem in time, we have a single initial condition. Okay? And the way we do that is to say that U, which can be a function of position, it is indeed in general a function of position, and this is what we saw in our steady state problems, right? So we have U as a function of, as parameterized by position, and at time t equals 0, okay, equals some U not function of position only, okay, right? And perhaps this is best clarified by also saying here that U is a function of position and time. Okay? All right. That indeed does complete the specification of our problem. The PDE, boundary conditions, and initial conditions. What I'm going to do here is just make one or two remarks. Okay, the first remark is that we need to say something about this new coefficient we've introduced, rho. Okay, for a heat conduction problem, right? For heat conduction problems, can you tell me what rho is? Yeah, for a heat conduction problem, rho would be the rho is the specific heat. Okay, and in the case of heat conduction, do you also know where our PDE comes from? What physical principle leads to our PDE? It's actually the first law of thermodynamics. Okay. So in that setting, rho is a specific heat. Okay, and the way we've written it, rho would be the specific heat per unit volume. Okay, so as we've written it, rho is a specific heat per unit volume. The specific heat also can be determined as can also be defined per unit mass. Okay, but in our setting, for the way we've set up the problem, rho is a specific heat per unit volume. All right. It turns out that if, however, we were looking at the mass diffusion problem, is equal to 1. Okay, we don't need a notion of anything like a specific heat in the context of mass diffusion. Mass diffusion just arises from a physical principle, which is the conservation principle. Okay, so that is the setting for this problem. Sorry, that is the sort of setting of context for the physical problems. Okay, so let me see, is there anything else we need to really talk about here? Actually, I believe not. So we have laid down our strong form of the linear parabolic PDE in a scalar variable in 3D. It connects up with our heat conduction and mass diffusion physical problems. And we'll end the segment here. When we return, we will do the usual, take the usual steps that we've taken before, right? The weak form, and then talk about the finite element formulation.